So welcome to this webinar on optimizing processor cache on Z13 and Z14 processors. Processor cache utilization plays a significant role in CPU consumption for all Z processors, but that role became more prominent than ever beginning with the Z13. Achieving the rated 10% capacity increase on Z13s versus Z12s, despite a clock speed that was 9% slower, is very dependent on effective utilization of processor cache. So as Brent mentioned, this analysis began with a case study at my previous employer and has since been significantly expanded with insights gained from reviewing processor cache data from more than 50 sites across 5 countries. So in this webinar, we'll begin by discussing key processor cache concepts and metrics that lay the foundation for understanding the vital role processor cache plays in CPU consumption. Then we'll examine LPAR topology and see the significant impact it can have on cache efficiency. There's a lot of continuity in processor cache concepts between the Z13 and Z14, but we'll examine the key changes in processor cache design on the Z14 and see how these changes impacted the metrics in a Z14 case study. Finally, we'll leverage these metrics to show the positive impact on processor cache efficiency that can be achieved by maximizing the work that's executing on vertical high logical CPs through optimizing LPAR weights and increasing the number of physical CPs. And we'll be using numerous examples from real-life situations throughout the webinar to illustrate the potential impacts of these tuning actions. Most of the metrics we'll discuss come from the SMF 113 records produced by the CPU measurement facility. These metrics are essential to analyzing and optimizing processor hardware performance, so it's very important to have good visibility into this data. So the first metric we'll consider is CPI, cycles per instruction. This represents the average number of processor cycles spent per completed instruction. And conceptually, processor cycles are spent either productively, executing instructions and referencing data that's present in level 1 cache, or unproductively, waiting to stage data as a result of level 1 cache or translation look-aside buffer misses. So keeping the processor productively busy executing instructions is highly dependent on effective utilization of processor cache. Now I said conceptually a moment ago because even while waiting to stage data, Z processors leverage out-of-order execution and other types of pipeline optimizations behind the scenes seeking to minimize that unproductive waiting. So this chart from the IntelliMagic Vision product breaks out cycles per instruction into the productive and unproductive components that we just mentioned. The space above the blue and below the red line on this chart reflects the cycles productively spent executing instructions for a workload. This would be the CPI value if all required data and instructions were always present in level 1 cache. And it's called the Estimated Instruction Complexity CPI, because it reflects the mix of simple and complex machine instructions in your business workload. It may be impacted by migrations to new processor technologies that incorporate internal improvements in processor architecture, but otherwise it's likely to be relatively constant based on workload. But since reality is that we have a finite amount of level 1 cache, limited to a size that can be accessed in a single machine cycle, the area below the blue line reflects the cycles spent waiting for data to be staged from processor cache or memory due to level 1 cache misses, and it's termed the estimated finite CPI. So reducing these unproductive cycles is the focus of efforts to optimize processor cache. So this chart represents one of the primary takeaways of this entire webinar. These waiting on cache cycles represent a very significant portion of the overall CPI, typically ranging from 1/3 to, in some cases, more than half of total CPU consumption on Z13 processors. So that establishes the magnitude of the potential opportunity if improvements in processor cache efficiency can be achieved. So fortunately, IBM provides a metric that correlates closely with the unproductive cycles represented by that blue line, and that is relative nest intensity, RNI. That quantifies how deep into the shared processor cache and memory hierarchy, which is called the nest, the processor needs to go to retrieve data and instructions when they're not present in level 1 cache. This is very important because access time increases significantly for each subsequent level of cache and thus results in more waiting by the processor. The formula to calculate RNIs provided by IBM is processor dependent and reflects the relative access times for the various levels of cache. This is the z13 formula. Retrievals from chip level, level 3 cache, L3P, level 3 percentage, are quicker and thus have the relatively low weighting of 0.4. Retrievals from cache local to the node where the processor core resides, L4LP, have a higher weighting factor. Retrievals from cache remote from that node, L3RP, level 3 remote percentage, take more cycles. And finally, retrievals from memory, as reflected by MEMP, have a weighting factor that's almost 19 times higher than the factor for chip level, level 3 cache, reflecting how many more machine cycles are lost waiting for data when it's not found anywhere in cache and must be retrieved from memory. Now here's the RNI formula for the z14. It's similar to the z13, but note the significantly lower penalties for remote cache and memory accesses highlighted in green, which we'll discuss in more detail a bit later. So IBM defines a threshold value for RNI of 1.0, above which a workload is considered to place a high demand on cache and thus may not achieve the rated capacity of a processor. But no matter what your RNI currently is, reducing it means less unproductive waiting cycles and more processor efficiency. This IntelliMagic Vision chart apportions those waiting cycles of estimated finite CPI across all the elements of the cache hierarchy and estimates the relative contributions of each to CPI. So we'll talk more about the specific elements of the cache hierarchy in a bit. But since almost all of these components of cache misses are part of the shared cache hierarchy and thus incorporated into the RNI metric, reducing RNI means reducing these unproductive cycles spent waiting for data to be staged from processor cache and memory, improving CPI and thus processor efficiency. Now, this RNI-driven component often represents about half of the overall CPI, which is the basis for the rule of thumb that a 10% reduction in RNI can be expected to result in a 5% reduction in CPU. If the waiting cycles in your environment are somewhat lower, then you can adjust that rule of thumb accordingly. So how can we go about reducing RNI? Well, a key concept to understand if we want to do that is hyperdispatch. Hyperdispatch has been around for a long time, but it plays an even more vital role in the z13 and z14 processors where cache performance has such a big impact. Hyperdispatch includes many technologies, but the aspect pertinent to our discussion today is the Prism and ZOS dispatchers interfacing to establish affinities between units of work and logical CPs and between logical and physical CPs. This is important because it increases the likelihood of units of work being redispatched back on the same logical CP and executing on the same or nearby physical CP. That optimizes the effectiveness of processor cache at every level by reducing the frequency of processor cache misses and by reducing the distance into the nest required to fetch data when a miss occurs. When hyperdispatch is active, Prism assigns logical CPs as vertical highs, mediums, or lows based on LPAR weights and the number of physical CPs. Vertical high logical CPs have a one-to-one relationship with a physical CP. Vertical mediums have at least a 50% share of a physical CP. Vertical lows have no guaranteed share. They exist to exploit unused capacity from other LPARs who are not using all of their share. Work executing on vertical highs optimizes cache effectiveness because its one-to-one relationship with a physical CP means it will consistently access the same processor cache. On the other hand, vertical mediums and vertical lows may be dispatched on various physical CPs where they will be contending for processor cache with workloads from other LPARs, making the likelihood of their finding the data they need in cache significantly lower. So this set of charts from IntelliMagic Vision builds upon the raw metrics that are in the 113 records to estimate the lifetime of data in the various levels of processor cache. And it's graphed by processor over, in this case, a 24-hour time interval, and it provides another data point reinforcing the importance of reducing cross-LPAR contention for cache. In this environment, cache working set data remains in level 1 cache for less than 1/10 of a millisecond, in level 2 for less than 2 milliseconds, or in level 3 around 10 milliseconds during prime shift hours. So if a vertical medium from LPAR 1 gets redispatched on a physical CP after LPAR 2 executed there for even a single prism time slice, which is typically 12.5 milliseconds, its data in level 1, level 2, and level 3 caches will all be gone. Now the good news is those working sets can be rebuilt from level 4 cache, but the bad news is each access to level 4 cache may take 100 or more cycles. So this reinforces the importance of having as much work as possible executing on vertical high CPs and thereby eliminating contention for processor cache from other LPARs. So let's see if this hypothesis that work executing on vertical highs experiences better processor cache performance is validated from the SMF 113 record. So this chart compares RNI values for a production system, we'll call it System 3, on a Z13 across 2 separate days. The first day, the system had a vertical CP configuration of 3 vertical highs and 2 vertical mediums, and on the second date, the configuration had changed to consist of 5 vertical highs. So the significant reduction in RNI is apparent. Now this chart showing RNI for the same dates and system but now by logical CP is very informative because it confirms that the 2 vertical medium CPs, CPs 6 and 8, the light blue and green lines at the top of the before chart on the left, had the greatest reductions in RNI. When they were running as vertical mediums, they had higher RNIs than the vertical highs because they were competing for processor cache with other LPARs. When the configuration changed on the after chart on the right, such that CP 6 and 8 were now also vertical highs, their RNIs decreased significantly to a level comparable to the other vertical highs. RNI improves when work can be moved from vertical mediums to vertical highs. And we'll see examples later where this RNI gap between vertical highs and vertical mediums is even more pronounced when adverse LPAR topology comes into play. So here are examples from 4 other Z13 sites, all also reflecting measurable differences in RNI values between the vertical highs and the vertical mediums. The first example, there's a 57% difference. The second example, a 22% difference. Then a 113% difference. And finally a 15% difference. So in each case, the identification of vertical highs and vertical mediums is apparent on the chart from the differences in the RNI values. And here are examples from 4 more Z13 sites, 22%, 38%, 41%, and 22%. So just confirming this a very widespread experience, work executing on vertical highs experiences significantly better RNI values since it's protected from cross-LPAR contention for processor cache. So far, we've seen from looking at the processor cache concepts and metrics that CPI and thus CPU consumption decreases when we reduce unproductive machine cycles waiting for data and instructions to be staged into level 1 cache. And this effort to optimize processor cache is worth investigating. It's important to have good visibility into processor cache metrics because lots of cycles are at stake. Those unproductive waiting cycles typically represent at least 1/3 of overall CPU and often 1/2 or more. Fortunately, our mainframe world is very metric rich. We have access to the R&I metric that correlates to those unproductive waiting cycles. Reducing R&I reduces CPU and thus MLC software expense. And optimizing processor cache can have a particularly big payoff on Z13 processors, which are more dependent than ever before on effective cache utilization. So now we'll turn our attention to the significant impact LPAR topology can have on R&I. Prism dynamically assigns LPAR CPs and memory to hardware chips, nodes, and drawers seeking to optimize cache efficiency. This topology can have a very significant impact on processor performance because remote cache accesses can take hundreds of machine cycles. Topology data is provided by the SMF Type 99 subtype 14 record. Now, as opposed to some of the other subtypes of the SMF 99, which can generate overwhelming volumes, subtype 14 is very manageable, one record per logical CP every 5 minutes. So this is another data source that you want to ensure you are collecting and analyzing. So this IBM Z13 drawer cache hierarchy diagram will be very helpful in establishing a framework for understanding this LPAR topology discussion. So a Z13 has 1 to 4 CPU drawers in a CAC, along with some number of I/O drawers, and 2 nodes in a drawer. Each active physical CP, which is labeled a PU core here, has its own dedicated level 1 and level 2 cache. So let's assume a unit of work is executing on processor unit core 1 in single chip module 1, pointed to by the arrow. Now when it accesses level 3, the first level of cache that is shared, and thus is part of the nest and thus the R&I metric, that access can be either on chip or on node, on a different SCM within this node, or on drawer, on the other node in this drawer, or off drawer, to some other drawer not represented in the diagram. Remember, the more remote the access, the greater the number of machine cycles required for that access. Similarly, access to level 4 cache can be on node, on drawer, or off drawer. And then finally, access to memory, on node, on drawer, or off drawer to some other drawer not shown in this diagram. So here's a sample report of data from the 99.14 records. For each logical CP, its chip node and drawer are listed under the gold arrows. Now we're going to analyze data from 2 scenarios where LPAR topology has a significant impact. And there's a third scenario that will be in the backup slides. To do that, so let's view the LPAR topology information in a more visual format. So for scenario 1, this diagram presents CP placements for all the LPARs on a Z13 711. Each entry here represents a general purpose logical CP, and it indicates its sysID, its polarity, vertical high, vertical medium, or vertical low, and relative logical CP number starting from 0 for each polarity type. The vertical highs are highlighted in bold. ZIP CPs have been removed because our analysis is focused on general purpose CPs. The same concepts apply to ZIPs as well. So in this scenario, the logical CPs from several LPARs are competing for physical CPs on 3 chips across 2 drawers. Now I added green and orange shading to compare and contrast 2 primary production systems, systems 3 and 18, that execute similar data sharing workloads. both having 3 vertical highs and 2 vertical mediums. Now note that the vertical highs and vertical mediums for System 3, shaded in green, are co-located on the same chip. Now we viewed the RNI biological CP chart for this system earlier. You may remember that the RNIs for the 2 vertical medium CPs on this system were higher than the vertical highs, but not dramatically so. Now contrast that to the topology of System 18 in orange, which has 3 vertical highs in drawer 2, but its 2 vertical mediums reside in a different drawer, drawer 3. Not just a different chip in the same node or not a different node in the same drawer, but in the most remote possible location in a different drawer. So in light of the fact that cache references from the vertical mediums on System 18 will routinely have to traverse across drawers, how do you expect that will impact RNIs for those vertical mediums? So note the extent of the negative impact to RNI for the 2 vertical mediums, CP 6 and 8, again light blue and green at the top of the before chart on the left. The gap between the vertical mediums and the 3 vertical highs is much larger on this system with the adverse LPAR topology than it was on System 3 that we saw earlier, where the vertical highs and vertical mediums were co-located on the same chip. And the improvement in RNI when CP 6 and 8 changed to become vertical highs was even greater, because it is very likely now that all 5 of these vertical highs are co-located on the same chip. Here's another IntelliMagic Vision chart that breaks out the weighting cycles of CPI by the various causes and shows the impact of all that far slower off-drawer access on System 18's CPI, the bar on the right. Note the significant increases in cycles spent on off-drawer accesses for System 18, for Level 3 cache in gray, Level 4 cache in the light blue, and memory in the dark blue. In particular, the cumulative impact of the Level 3 and Level 4 off-drawer accesses added more than half a cycle per instruction for System 18 as compared to System 3. And drilling into this cache miss data on System 18 biological CP demonstrates how those off-drawer accesses predominantly occurred on the 2 vertical medium logical CPs, CP 6 and 8, as we would expect. Note that the work executing on those 2 vertical mediums required 2 full additional cycles per instruction compared to work executing on the 3 vertical highs due to the adverse LPAR topology. So another key takeaway here is that when there's a significant disparity between the RNIs for vertical mediums and vertical highs on the same system, it warrants investigating the LPAR topology. And this highlights another benefit of having more work executing on vertical highs. In addition to avoiding cross-LPAR contention for cache from other LPARs, as we discussed earlier, a second benefit is that since PRISM is very likely to co-locate vertical highs, the incremental work now executing on these vertical highs will most likely not be subject to cross-node or cross-drawer access times often experienced on vertical mediums. Now, a second LPAR topology scenario involves an entirely different kind of opportunity. In this environment, PRISM configured all 10 vertical high logical CPs from 2 primary online LPARs in the same node on the same drawer, with the outcome that they were sharing the 480 megabyte level 4 local cache of that single node between them. After reviewing some internal configuration data, IBM advised that increasing the memory allocation for each of these 2 LPARs by a few gigabytes would cause them to exceed the memory available in a single drawer and force PRISM to assign them to separate drawers. So after making that change, PRISM did indeed distribute the vertical high CPs for those 2 LPARs across separate drawers, which doubled the amount of level 4 local cache that they now had access to. So what kind of impact on RNI do you think a change like this would achieve? Well, now that these CPs had twice the level 4 local cache available to them, we'd expect more misses to be resolved from level 4 local cache. Now I included the Z13 RNI formula again here to remind us how much lower the weighting is for level 4 local hits than for level 4 remote and memory. An additional 1.5% of level 1 misses were now sourced from level 4 local cache, the L4LP in green, reducing the frequency of trips to remote cache and especially to memory. This resulted in an 11.5% reduction in RNI, and IBM measured a corresponding 6% increase in effective capacity as a result of this single topology change, a change that did not require deploying any additional hardware but only involved utilizing the existing hardware more effectively. So another key takeaway is that LPAR topology can significantly impact processor cache efficiency. All right, so now let's look at the processor cache design changes on the Z14 and then see the impact of those changes with a case study from a site that has implemented a Z14 in production. We'll list several significant design changes and then look at each one in some more detail, along with its associated metrics. First, a unified level 4 cache enables point-to-point access to remote drawers, which reduces the cycles required for remote drawer access as compared to the Z13. Z14 also delivers changes to the Prism LPAR algorithms designed to reduce cache waiting cycles. One change prioritizes the effort to fit an LPAR within a single drawer, seeking to reduce expensive remote accesses. The increase from 8 to 10 cores per chip makes this more achievable by increasing the size of an LPAR that will now fit within a drawer. Another Prism algorithm change now prioritizes placing GCPs, vertical highs and vertical mediums, in close proximity on the same chip or cluster, in contrast to the Z13, which prioritized co-locating vertical highs for both GCPs and zips. Z14 also includes strategic increases to selected cache sizes, and finally, the level 1 translation look-aside buffer was merged into level 1 cache, eliminating level 1 TLB misses. So in this Z14 cache hierarchy diagram, we find a cache hierarchy in levels 1 through 3 that's largely similar to the Z13. But one very significant difference is the unified level 4 cache. So let's look at the rationale behind that. Looking at drawer interconnects across the Z processor technologies, ZC12 and prior models provided point-to-point connectivity between all books at the time, now called drawers, enabling all accesses to remote cache to be reached directly. But on the Z13, depending on the node in which the data resided, remote accesses could now require multiple hops and thus require hundreds of machine cycles. This helps explain why LPAR topology plays such a major role in RNI on the Z13 and why some high RNI workloads had performance challenges migrating to the Z13. The Z14 design unifying the level 4 cache and the system controller restores point-to-point connectivity between all the level 4 caches. So the first two design changes, point-to-point access and changes to LPAR placement algorithms, were designed to reduce the frequency of remote cache accesses and to reduce the cost of the remote drawer accesses that still take place. So let's look at the impact of those changes in a case study from a site that has a Z14 in production. Now again, as we look through these metrics, they're based on findings from a single site. They clearly reflect the impact and value of the Z14 changes, but keep in mind they may not represent the experience of every site. Your mileage may vary. This is the RNI biological CP for a large LPAR when it was running on a Z13. Note the very significant RNI penalty for the vertical mediums along the top of the chart compared to the vertical highs. This was a frequent occurrence for dominant LPARs on Z13s, where the LPAR topology commonly located vertical mediums in a separate drawer from the large number of vertical highs. Now note the significant change when this LPAR migrated to a Z14. The RNI penalty for the vertical mediums was dramatically reduced. Here are those metrics in tabular form. The RNI penalty for the vertical mediums went from 87% on the Z13 to 23% on the Z14. And from our earlier discussions, you may be able to anticipate what the underlying LPAR topology changes appear to be. Here's the LPAR topology diagram for this LPAR when it was running on a Z13. Note that the vertical mediums in orange are in a separate drawer, drawer 2, from all the vertical highs in green in drawer 3. This led to frequent cross-drawer accesses by the vertical mediums and thus the significant RNI penalty they experienced. Now note the changes in the LPAR topology diagram for this LPAR on the Z14. Now the vertical mediums in orange and vertical highs in green are in the same drawer and even share the same level 3 cache. In fact, PRISM was able to configure the entire LPAR, GCPs, and zips in a single drawer. Now I include this topology diagram from later that day, again on the Z14, to highlight 2 points. First, PRISM can make dynamic changes to LPAR topology. In this case, the change was likely driven by the fact that additional zips were configured online. Note that now the LPAR is located in an entirely different drawer. Now it's in drawer 4 versus drawer 2 earlier. But again, all the GCP, vertical highs and vertical mediums, are still co-located in close proximity. Again, same drawer, same level 3 cache. Only the home location of the vertical low is elsewhere, but vertical lows can be dispatched anywhere based on the location of the donor LPAR. And in any case, it's likely to represent a very small workload. So here's another key takeaway. The PRISM algorithm changes on the Z14 resulted in a very positive outcome for this dominant LPAR, reducing the RNI penalty for vertical mediums dramatically because of improved proximity in the LPAR topology. The Z14 delivers several cache size increases as highlighted here in green. The increases are in level 1 instruction cache, 1/3 larger, level 2 data, which doubles, and level 3, which doubles. We mentioned earlier that the Z14 cache has been unified, enabling point-to-point connectivity between all the level 4 caches. IBM's analysis says this reduced latency for remote cache accesses more than offsets the decrease in the size of level 4 cache from 960 megabytes spread across 2 separate nodes on the Z13 to a single 672 megabyte cache on the Z14. So now let's look at a case study of the cumulative impact of all these changes on the Z14 cache metrics and overall delivered capacity. These charts show the estimated lifetime of data in the various levels of processor cache for both processor models. The duration that data remains in cache on the Z14 is at least 50% longer for levels 2, 3, and 4, which we can certainly expect translates into lower miss percentages and thus better RNI. This shows the very positive impact of the Z14 on some of the key cache and TLB metrics. The level 1 miss percentage, which is one of the 2 primary variables in the IBM LSPR chart classifying workloads as high, medium, or low complexity, decreased from 3.85 to 3.17%, likely reflecting the increased size of the level 1 instruction cache as well as other architectural improvements. The contribution of TLB miss cycles to overall CPI, which is a subcomponent of the weighting cycles of estimated finite CPI, decreased significantly, showing a very positive impact of merging the level 1 TLB into level 1 processor cache. Another positive impact of that merge is seen in the fact that total CPU consumed for TLB misses decreased by more than half, from 5.8% to 2.7%. And machine cycles spent when there was a TLB miss also decreased as shown. Continuing the story of the very positive impact of the Z14, here we see total CPI, the red line, estimated finite CPI or waiting cycles, the blue line, and the TLB miss cycles in yellow. The story here is the change in scale. The CPI went from around 3.5 on the Z13 to under 3 on the Z14, with corresponding decreases in the other two metrics. Here's the table breaking out the contributors to that impressive reduction in overall CPI. Instruction complexity CPI reflected the impact of architectural enhancements in the Z14, resulting in fewer cycles being required to execute the instructions for this site's business workload. A greater contributor here to the improvement in CPI was the reduction in waiting cycles associated with the cache hierarchy, helped by the reduction in the VM penalty we saw earlier, along with the improvement in the TLB miss subcomponent. So finally, let's translate this sizable CPI improvement into its impact on delivered capacity. So the inverse of CPI is the number of instructions completed per machine cycle. And the cycle speed on the Z14 is approximately 4% faster than the Z13, 4% more cycles per second. So converting that into a number of business instructions being executed per second, here in billions, represents a 31% increase in delivered capacity. The difference in the rated capacities, MSUs per CP, of the Z13 and Z14 processor models deployed here was approximately 13%. So this site is experiencing a much bigger lift in delivered capacity from the Z13 to the Z14 than would be anticipated by the processor rating. Now the overall workload at that site was borderline high from an R&I perspective. And in Gary King's presentations, he indicates that high R&I workloads can anticipate experiencing a bigger performance gain migrating from Z13 to Z14 than other workloads, since the Z14 includes a number of design changes to reduce processor cache latency, especially designed to help high R&I workloads. But this was an even more positive result in this particular environment. And this continues the common pattern where workloads that had smaller gains with one processor generation often experience bigger improvements in the next generation, as design changes tend to focus on the challenges faced by the previously disadvantaged workloads. All right, so returning now to a key concept from earlier in the webinar, maximizing the amount of work executing on vertical high CPs enhances processor cache efficiency, since it eliminates contention for processor cache from other LPARs, and since vertical highs are more likely to be co-located in the LPAR topology. So if we want to optimize vertical CP assignments and maximize the amount of work executing on vertical highs, there are two variables that come into play in how vertical highs are assigned: LPAR weights and the number of physical CPs. So let's consider each of these in detail. If you're not familiar with how Prism assigns logical CPs as vertical highs, mediums, and lows, it's covered in the backup slides from the webinar. So first, here are some ways LPAR weight values can be set to maximize the amount of work executing on vertical highs. One way is to adjust LPAR weights to increase the number of vertical highs for high CPU LPARs that currently have a significant workload executing on vertical mediums and possibly even vertical lows. We'll see an example of this on the next slide. Also, by tailoring LPAR weights, we may be able to increase the overall number of vertical highs assigned by Prism on a processor. And we'll see an example of this on a coming slide as well. If the characteristics of the workload on your LPARs change between shifts, automating LPAR weight changes corresponding to those shifts may be another way to increase the workload executing on vertical highs. And finally, Fewer larger LPARs may be a configuration option you can exploit to increase the amount of work executing on vertical highs. So this first use case involves a small weight change. Now notice with this vertical CP configuration for a large LPAR, the CP share is just below the cutoff point where an additional vertical high would be assigned. So a small LPAR weight change to increase the percent share for this LPAR from 70 to 71% increases the number of vertical highs from 7 to 8. This reduced the overall R&I for this large LPAR by 2% for the given measurement interval, which correlated to a 1% decrease in CPU. Now 1% less CPU in a large LPAR can translate into a meaningful reduction in MLC software expense, especially when compared with the level of effort required to identify and implement this type of change. Benefits from tuning LPAR weights typically produce single-digit percentage improvements, as in this case, but there can be larger opportunities. In this example, planning for a configuration change was underway, a change to split the primary production workload across 2 systems. So to prepare for this change, which would go live in a few months, a new LPAR was defined and activated, LP04. Now the opportunity here is that the entire production workload was still executing on LP01, which now only had access to 4 vertical highs, so that a sizable workload was executing on vertical mediums and vertical lows. After those LPAR weights were changed to reflect the current workload configuration, and now that the production LPAR could leverage 9 vertical highs instead of 4, the overall R&I for that production workload decreased by over 10%, which translates into a 6-figure annual reduction in MLC expense. Another example of changing LPAR weights to increase the number of vertical highs appears in the backup slides. Now, in addition to LPAR weights, the other variable that we can leverage to maximize work executing on vertical highs is increasing the number of physical CPs. There are several potential ways this can be achieved. One way is to increase the number of physical CPs is to opt for subcapacity processor models. Activating on-off capacity on demand during monthly peak intervals is a second approach to increase the number of physical CPs. And a third way is to install or deploy additional capacity. So let's review each of these in turn. If single engine speed requirements or other considerations in your environment don't require full capacity models, subcapacity models can be selected when upgrading to new generation technologies. This adds physical CPs along with the associated level 1 and level 2 processor cache without incurring additional hardware expense, which results in more vertical highs and thus reduced R&I. This chart shows various z13 models that have similar MSU capacity ratings as a z14 711. So opting for subcapacity models in this example would result in 7 to 15 more physical CPs than the full capacity 710, significantly increasing the available processor cache and workload executing on vertical highs, and likely then realizing more capacity from the subcapacity models, even though the rated capacities were very similar to the z13 710. IBM MLC software expense is determined by the peak 4-hour rolling average for the month. So if your monthly peaks occur at predictable time intervals, on-off capacity on demand can be activated during those peak intervals with minimal incremental hardware expense. The impact of deploying this additional capacity on processor cache is more physical CPs, which means more vertical highs, and thus more of the work executing on vertical highs, which reduces R&I, which reduces CPU, and which, since it's deployed at the monthly peak, translates directly into reduced MLC software expense. In the backup slides, there's a case study of a site that's utilizing this to achieve, again, 6-figure annual savings in their MLC expense. A third way to increase the number of physical CPs is to install or deploy additional surplus hardware capacity. Now, traditional hardware capacity planning has been predicated on the assumption that running mainframes at high utilizations is the most cost-effective way to operate. But the results of the case studies in this presentation challenge that approach and strongly suggest that in many cases significant reductions in MSU consumption and thus MLC software costs may be achieved by operating at lower utilizations, particularly due to the increasing impact that cache utilization has with the z13 processors. Developing the business case to acquire additional hardware capacity may be challenging, but many sites would not require that business case since they already have a business practice of pre-purchasing additional capacity that they don't immediately deploy for reasons including negotiating a volume discount or a long-term lease, minimizing procurement effort involved with frequent acquisitions, or acquiring capacity required for seasonal peaks, which is then deactivated for the remainder of the year. But these sites tend to deploy that previously acquired capacity in a just-in-time manner rather than reaping the recurring benefits of MLC software savings by deploying surplus capacity as soon as it's acquired. In many cases, the driver of this just-in-time approach is independent software vendor licenses, which I'll speak to shortly. So in either case, whether acquiring additional hardware capacity or deploying previously acquired capacity, the framework for reevaluating this approach is that in most mainframe environments, software represents a much larger expense than hardware. And if a one-time hardware acquisition expense achieves software savings which are realized on a recurring basis year after year, there may be a strong business case for acquiring or deploying hardware capacity that significantly exceeds your workload requirements. Customers indicate that capacity-based independent software vendor licenses can be a primary barrier to deploying owned capacity or to considering acquiring surplus capacity because many ISV contracts are capacity-based and not usage-based. Those capacity-based ISV contracts will severely limit your ability to configure your environment in the most cost-effective manner until you renegotiate them to be usage-based. So I encourage you to tackle that proactively and aggressively. At my previous employer, we converted all ISV contracts to be either enterprise or usage-based. It can be done, and it will position you to have options for substantial financial savings going forward. I'm going to conclude with a use case showing the impact of deploying hardware on processor cache efficiency and CPU consumption. And there's a second use case in the backup slides. So this use case involves a high R&I workload and hardware capacity that had been previously acquired but not deployed. Employs a set of weekly tracking charts comparing the production business online workload in millions of transactions, which is the red line, versus CPU consumption, the blue line. For the last several months in a ZEC12 environment, these values tracked very closely. But after all four processors had been upgraded to Z13s by the end of this interval, MIPS consumption, the blue line, was far exceeding the business transaction workload, the red line. As we said, on Z13 processors, the cycle speed is 9% slower, but rated capacity is 10% higher. And the R&I workload in this environment did not achieve the improvement in cache effectiveness that the Z13 relies upon to achieve this increased capacity. So that resulted in a capacity shortfall of 4,000 MIPS versus the ZEC12 configuration. Now, when additional hardware was deployed that enabled most of the workload to execute on vertical highs, MIPS consumption, the blue line, was reduced dramatically, resulting in a 9,000 MIPS savings versus the Z13 711s for equivalent business workloads, which was a net 5,000 MIPS savings from the starting point of the ZC12s. Ultimately, all the previously acquired capacity was deployed through upgrades to 726 models, further reducing MIPS consumption, the blue line. So this resulted in an additional 4,000 MIPS savings versus the 716s, a 13,000 MIPS reduction from the 711, and a net 9,000 MIPS savings from the ZEC12 starting point, which, as you can imagine, is resulting in substantial MLC savings every year going forward. Now, the primary factor driving this final round of savings was not processor cache efficiency, but a reduction in the MSU per CP ratio, which we'll now discuss. Another important factor impacting measured CPU consumption that adds to the business case for acquiring or deploying additional hardware relates to the multiprocessing effect. The MP effect applies to any hardware environment, reflects the fact that adding cores or CPs increases the overhead required to manage the interactions between physical processors and shared compute resources. So to account for this MP effect when running at high utilizations, the MSU per CP ratios in IBM's processor ratings are not linear but decrease significantly as more CPs are added. But if a site's workload remains the same when CPs are added, overall processor utilization will decrease and additional overhead from the MP effect may be negligible. So in that case, a lower MSU per CP rating translates directly into lower MSU consumption for the same workload. This chart compares MSU per CP factors for the 4 processor models in the previous use case. The orange value showed the 10% plus increase associated with the original z13 711 implementation, one that the high R&I workload fell far short of achieving. The green value shows the decrease of 18% in the MSU per CP rating for the 726 from the 711. Or expressed another way, a workload that would generate 1,000 MSUs on a z13 711 would generate only 819 MSUs when run on a 726, solely due to the reduced MSU per CP rating, not even taking into account the CPU savings from improved processor cache efficiency that, as we saw, would also accompany this change. So there's a 1-2 punch in terms of the benefits of deploying additional hardware capacity while running at lower utilizations. First, less CPU is consumed due to operating efficiencies from more effective use of processor cache and other operating system efficiencies through optimizing LPAR topology and maximizing work executing on vertical highs. And second, the CPU that is consumed translates into fewer MSUs due to the decrease in the processor MSU per CP ratings. Here's what another author wrote recently, and I quote, "Acquiring more hardware capacity than needed to support the workload allows multiple benefits. First, it enables taking advantage of the lower MSU per engine rating of larger processor configurations. And second, it enables benefits from the impacts of low utilization on processor capacity." So other than reversing the order of the bullets, that's almost a repeat from the previous slide. Any guesses who wrote this? IBM distinguished engineer Kathy Walsh in a recently revised white paper. Details for accessing that paper are on the sources slide at the end. So this business case of achieving software expense reductions by deploying additional hardware can be so compelling that Frank Kine reported in the most recent Cheryl Watson tuning letter that in Europe, IBM is offering customers loaner capacity at no cost so they can validate and quantify the extent of the savings in their own environments with their own production workloads. So in summary, in our webinar today, we covered key processor cache concepts and metrics like CPI and R&I, and how they give us great insight into the unproductive machine cycles spent waiting for data and instructions to be staged in a level 1 cache. And this confirmed the value of seeking to optimize processor cache, since those unproductive waiting cycles typically represent 1/3 to 1/2 or more of overall CPU. That's why it's so important to have good visibility into processor cache metrics, the kind of visibility that, as we saw today with the various charts that IntelliMagic Vision provides. Then we examined how LPAR topology can have a very significant role in processor cache efficiency. We reviewed the several cache design changes on the z14 and saw how several of those are especially designed to help high R&I workloads. And the case study showed that the z14 changes had a very positive impact in that environment. And finally, we reviewed ways to maximize work executed on vertical high CPs through optimizing LPAR weights and increasing the number of physical CPs. So the references to the sources that I mentioned today are in the slides when you receive a copy of that. And here are some additional resources, and I'll hand it over now to Brent.
Very good. Thank you, Todd. Very valuable content. We will take a couple of questions. Go ahead and submit questions. If you have some more, we won't have time for all of them, but we will respond in writing if you have some questions. We also will send out a link to the recording after the webinar and a PDF of the slides as well. And once we end the webinar, there is a survey. We would appreciate it if you have comments or suggestions. We will look at those. Please answer those questions as well. With just a little bit of time here, Todd, I wanted to ask one of my questions first. If you could just speak very briefly on the role that IntelliMagic Vision can play in optimizing CPU efficiency and reducing MLC. Do you have a couple of comments based on your experiences?
Yeah, so because this plays such an important role in overall CPU consumption, and thus MLC, there are a significant number of charts that are built into IntelliMagic Vision to give you visibility into these important metrics. For example, the RNI biological CP, the impact of the cache misses, biological CP, which can show the impact of adverse LPAR topology, charts that show the distribution of workload MIPS by polarity, high, medium, and low across your LPARs, which can kind of right at a glance show you if you have an opportunity to adjust LPAR weights to improve your overall amount of work executed on vertical high. So there's a lot of functionality built in because this is such an important area. We want to have this information right at your fingertips.
Yeah, excellent. So besides the resources that are mentioned on this page, that's a video and a white paper, there's other information available in that last link, but the third link down there talks about an MLC assessment as well. So if you're interested in seeing this kind of information that Todd is talking about with your own data from your own environment, for at least sites here in the Americas region, we do offer that for qualified sites for no charge. So you can find information about what data types are necessary and how that works, and please explore that if you have some interest in that. Here's a question that I like, Todd. In your experience across different environments, how common is it to identify processor cache inefficiency that can be feasibly addressed to reduce MLC? So maybe you could mention like how many of these kinds of assessments that I was just talking about we've done, and how many had some significant savings that you were able to identify.
Well, we've done over 50 of them now. There are, I don't have the, in 80+% of the assessments we identify some significant MLC opportunity, but they're spread across many areas, so I don't know exactly how many are processor cache related. There are a number, and then in other places, people have a good setup, but they don't have the visibility that reaffirms or confirms it to them, or they're considering a migration to a different processor technology or different changes in their LPAR configurations. So all of which just really underline the importance of of having visibility and having a setup that you're really maximizing the amount of work executing on vertical highs.
Yep, great. So we're a couple minutes after. We'll take a couple more questions if you can stay on, then we'll end it shortly here. But have you done any studies on the RNI aggravation seen due to zip-eligible work being redirected to the CPs?
I am not aware of how I would be able to isolate the impact of that work on the RNI of the general purpose CPs. Being able to have visibility into how much of that work's happening is very important. because it's it's a prime MLC savings opportunity, and with IBM's recent APAR that allows you to specify that now at the service class level, zip honor priority at the service class level, you have much greater control over that. So having visibility into that is great, but I am not aware of how I would quantify the impact of that on R&I. I mean, the basic thing is just get that work running on zips, and then now it's completely free.
Yeah, very good. Okay. How do sysplexes affect these metrics?
I mean, almost every site we look at is running in a sysplex, but the vertical CP configuration is determined by system, by LPAR, as based on the LPAR weight and the number of physical CPs on the processor. So the R&I analysis is primarily focused at the system level, whether the other systems in the sysplex, it's an independent thing. Now, if you are in a sysplex, there may be other opportunities for MLC software reduction. For example, to configure an LPAR with a limited software suite and run work that's eligible to run there rather than on LPARs with the full software suite can be a very significant way to achieve MLC savings. But that the R&I situation is independent by system.
Okay. It's just about 5 after the hour. We'll do this last question, and then we'll wrap it up. How effectively does WLM control LPAR weights on the Z13? If you change them, hoping to manage the work better, how do you keep WLM from altering your changes?
Well, WLM by itself doesn't do that. I believe that there is probably a reference to IRD, Intelligent Resource Director, which does change weights between LPARs, and or has the capability to, at least, and that is based on WLM performance indexes for WLM key, WLM service classes. So then a site has to weigh the benefits of the whether they need the IRD to manage the CPU to dynamically change the weights and to get the performance they need, or whether there's a value of just managing the weights directly so that you can have more control over your vertical CP configuration. The material we talked about in the last part of this webinar, which talks about the value of additional hardware capacity, can really help reduce overall CPU. If you're running an environment with some more of that hardware capacity, then you would not need RRD, because you would not be running at the high utilization levels that that need our IRD to be dynamically moving CPU between LPARs.
Very good. Okay, with that, we'll wrap it up. Todd, thank you very much for your content and presentation and expertise. Very, very good. Thank you, everybody, for attending our webinar today. And please stay on to answer the survey questions, and we will send you a copy of the recording today of the audio with the slides, as well as the PDF of the additional slides that Todd had mentioned. Thank you very much.